Welcome everyone. Today we are looking at the nature of light. You've done it before in your curriculum. You've spoken about light being a wave. You've spoken about light being a particle. But what does that actually mean? Well, let's look at that, shall we? So, what we're actually getting to is, have you ever thought about how solar panels work? Solar panels have become a big thing for us because it's renewable energy. It's cheaper energy. It's a way to power things. But how do they work? What is their principles? Why are they so exciting? That's what we're going to investigate today. We are looking at optical phenomena. So we're going to look at the nature of light. We're going to do some revision of waves. We're going to do the photoelectric effect. We're going to do the photoelectric equation. We're going to look at how it affects current. And then lastly, we're going to look at spectra. Not all in this lesson, though. So the key words for today are wave. What is a wave? Frequency, amplitude, wavelength, wave speed. None of these should be new. You've seen these somewhere in your curriculum at some stage. And then the new one is photoelectric effect. That is new. So that's what we're going to look at today. So let's talk about the nature of light. Light has a wave nature, which you've done in previous years, and it has a particle nature, which you've also looked at in previous years. So the first thing we need to look at is, what does it mean when we say it has a wave nature? Well, waves can do certain things that only waves can do. The first one is refraction. Remember, refraction is when you have light come to a boundary. This is how you would have investigated it. And the light hits at an angle and then changes direction. So refraction of a wave is when the wave goes from one medium to another medium, and it bends as it goes through because its speed is changing. Only waves can do that. It's a specific property of waves. The other one is interference. Now, interference is when two waves meet, and either they have constructive interference, so they make each other bigger, or they have destructive interference, so they make each other smaller. But only waves can exhibit interference. The next one is diffraction. Now that's something also that only waves can do. And to put it into an example for you, when you're looking through the windscreen or the window of a car at night, and you look at a street lamp, and it looks like it's got a halo, like it's all fuzzy around the ends. That's because the glass of the window has tiny little scratches in it. And as the light from the street lamp hits the glass, that light makes the wave diffract. It bends it. And that's the diffraction. So it's a little like refraction, but diffraction doesn't change the speed of the light. It just changes its direction. That can only happen with waves. Now, light can do all of this. It can be refracted, it can be diffracted, and it can exhibit interference. That tells me that it has a wave nature, okay? But light, when we look at the photoelectric effect, this is only possible if light is a particle. And we're going to prove that later on. And this has been a debate in the science community, well, it was, for a very long time, for hundreds of years. Some scientists said it's a particle, some said it's a wave. They agreed on one, then they agreed on the other, and it was a big mess. Then along came a scientist called Max Planck. He did some work, and then Einstein, we all know about Einstein, he added to it. And eventually scientists agreed. Light is both a wave and a particle. That's difficult to put in our heads. It's a hard thing to grasp. But sometimes we've just got to accept it. So, let's just remind ourselves of some important things about waves. They have frequency, they have a wavelength, there's going to be an amplitude, and then there's the wave equation. So remember, frequency, which is little f, is the number of complete waves that pass a point per second. It's like we count the waves, okay? It's measured in hertz. Capital H, little z, okay? It's named after someone. If you think of a radio station, it's normally at a certain frequency that we listen to it, and they describe that frequency in hertz. Normally in megahertz, maybe, so it's a big value. We're not going to worry about that, okay? Then there's wavelength, which is lambda. Just to remind you, lambda is like an upside down Y, okay? It's a Greek letter. Just learn the upside down. And lambda, so it's like a lamb with a DA at the end. Lambda. It's very weird. We learn Greek while we're doing science too. It's the distance between two consecutive points on a wave that are in phase. So if I drew a wave, that's a very bad one, but just go with it. It's from there to there. That's the wavelength, from the top of two crests or the bottom of two troughs. Doesn't matter. Then it's measured in meters. Here we need to be aware of the fact that distance is in meters, just like for everything else. Frequency is f, measured in hertz. Wavelength is lambda, measured in meters. In this section, we are going to be working with very, very small waves. So we're going to need to convert them to meters. And it also means that because the waves are so small, the frequencies are going to be very high. Okay? Then, of course, we get amplitude. And amplitude is the distance between the equilibrium position and the top of a crest or the bottom of a trough. That's the equilibrium position of my wave. This is a very badly drawn wave. That is my amplitude. It's like the height of a wave. So if you've ever watched on the news when there's a tsunami, for example, or you look at surfers, they wait for a wave that gets really high. They want a wave with a high amplitude. Okay, so that it goes high. It's a big distance from top to bottom, and it's the equilibrium position. Amplitude, when we look at our waves, is the same going up and going down, okay? We're going to use perfect waves because we're looking at light. We're not going to look at waves that do all sorts of weird and wonderful things because we don't want to. Wave speed is f times lambda. Okay, here we go. That's our wave equation, where speed is frequency times wavelength. You must keep this in the back of your mind. We're going to use it lots. So, the photoelectric effect is the process, and we're going to investigate this, so don't worry too much, that occurs when electromagnetic radiation, particularly light, shines on a metal surface and ejects electrons from the metal. And that's all I'm going to say about that for now, because we're going to investigate that after a short break. So I'll see you in a couple of minutes. Welcome back. Now, I mentioned what the photoelectric effect was. Now let's investigate it, because it's a wonderful concept and it's got so many applications for us. So, here we go. What we're going to do is we're going to look at a simulation which is going to help us. So, whoopsie, that's not the one I wanted. There we go. So basically what we have here is, this is a light source, okay, where I can change the light color of the light. It's going to shine on a piece of metal, which is over here. And what I'm going to look at is whether electrons get moved out of the metal, okay? And what we're going to look at is, does the brightness of the light make a difference, or does the frequency of the light make a difference? So I need to, it is actually switched on. Okay, so we're going to switch it on. And currently, there's no light. The intensity is 0. So let's make the intensity a little bit more. So there we go. Oh, look at that. Can you see? I have electrons moving. That tells me that this light is of such a nature that I can get electrons to move. And if I make the intensity very bright, it's not working that great, but they're actually going a little bit faster. We're not getting more, but they're going a little bit faster. Let's just make it go back to 50. Now, let's see what happens. There we go. If I change the frequency. Now, I'm going to change the frequency by changing the wavelength. And I need to remind you that wavelength and frequency are the inverse of each other. So if I make the wavelength bigger, I make the frequency smaller, okay? So let's make the wavelength bigger. And, oh, hang on, wait, look what's happened. Are we still getting electrons? Yes, but not as many. Can you see? Before we had lots, now we're not getting as many. Let's a little bit further along. Ooh, let's see, are we still getting? And we wait. Now they're moving very slowly, but I'm not getting any electrons now. So as I've made the wavelength bigger, I've made the frequency smaller, and there's this lone little electron. It's trying really hard to get to the other side. But what if we made the light brighter? Okay, because we know with normal waves, like if we think of a water wave in the sea, when the wave's got a very big amplitude, it's got lots of energy, and it's going to knock us over in the sea. So let's see if the same is here. So I'm going to make this very bright. Okay. No, nothing's happening. Maybe I should make the wavelength longer. No. Now I'm in the infrared. Nothing's happening. So it's actually not about the brightness of the light. It's about the wavelength, the frequency. So let's make this down here again. And we knew that when we started this, it was in this sort of range, and we got electrons, and this is for sodium. Let's make this even smaller. Let's see what happens. Look how fast they're moving. So much faster. Okay, and we're getting lots. Now if I increase the intensity, make it very bright, we're getting more electrons, and they're moving fast, and there's the current. You can see I'm reading a current. If I make it less intense, the current gets smaller. If I change the frequency, current's also going to get smaller. But I'm still getting electrons. Now the question is it the same for every metal? Because here I'm using sodium. So let's stop it. Let's go to zinc. And I'm going to start zinc over there. Okay. So no current. I expected that. Let's go, and with the sodium, it was about 500 nanometers that we got a current. Let's see what happens here. So I make this smaller. Oh, no current, no current, no current. Oh, look at that, no current. We get into ultraviolet. A little bit further, a little bit further. Let's see. Ooh, we can actually get there. Ooh, look at that. So to get current out of zinc, we need a very, very small wave. In other words, we need a wave with a very big frequency. Zinc and sodium allow electrons to move out of it at different frequencies. This is important to know because just because light shines on a metal doesn't mean that the electrons are going to come off it. There are characteristics of the light that's needed. There are properties that are needed, okay? Now again, so this current's still quite small, okay? If I go to the smallest I can make it on here, my current's still very small compared to what it was with sodium. I can make the current bigger by making the light brighter, but it still has the same velocity. That's quite important. If I go to copper, copper's got a much higher current at the same frequency. So let's see where copper stops. Already it stopped. Copper also is like zinc. What about gold? Oh no, platinum. Look at platinum. Ooh, platinum likes this. Platinum's nice for this. So if we do here, we can still get a current, still get a current, still get a current. Oh, there we go. But now, did we get a current from, oh, sorry, that's calcium, sorry, not copper. What am I talking about? There's sodium. Sodium, we got a current. So every metal will let me get a current at different frequencies, okay? Now, what is actually happening is the light is hitting the metal, and something is happening inside the metal that's causing the electrons to come off. We're having to give the electrons energy where they go, sorry, metal, you've been my home for a while, now I want to move on, okay? So let's look at that. All right, so how does it actually work? I'm just going to get a pen so we can talk about it. This is what's happening. Photons are coming. Photons are the beams of light. As they come in here, they are coming along here. They hit an electron, and then they push the electron out. Okay? So this is what's happening. They're coming along, and they're pushing. If light was a wave, this would not happen. The only way that can happen is this is a collision, like momentum. A particle is coming, hitting the electron with enough energy that it smacks the electron out of the metal, okay? Sometimes it only allows the electron to sit on the surface, so that's not very useful, but a lot of the times it can move apart. Now remember, if these electrons are moving, we have current. Current is the flow of charge. Now, I've just been calling them electrons. You'll see over there, it says photoelectrons. That's just because we have electrons that are being pushed out by a photon. Why is this important? It shows that light has a particle nature. Photons are particles. So, the minimum frequency of light needed, we talk about frequency, not wavelength, that's needed for an electron to be ejected from the surface of a metal is called the threshold frequency. Its symbol is FO. It's very, very specific. Now, every metal has its own threshold. So sodium is 5,5 times 10 to the 14. Zinc is 1 times 10 to the 15. And platinum is 1 times 10 to the 15. You don't need to know those values. Don't learn them. I just need you to see. For some metals, we can get it knocked out with visible light. Some metals, we use ultraviolet. And solar panels use ultraviolet. Okay, solar panels use this range just to because it's more effective. So, work function, new term. Minimum energy that an electron in a metal needs. So if we have a minimum frequency, and now we have a minimum amount of energy, they go together. The energy in light is measured by the frequency of the light, not the amplitude. So work function, now watch, we have an O. It goes with the threshold frequency. So WO is work function, measured in joules, because it's energy. Work is the transfer of energy. So we call this the work function because we're transferring energy from a photon of light, a particle of light, to the electron, okay? And this is the minimum energy to get it to sit on the surface. So it gets out, but it sits on the surface. H is Planck's constant. This is named after a scientist called Max Planck, a German scientist, and Einstein built on his work, where we get this, now we understand that light is both a wave and a particle. This constant, 6,63 times 10 to the minus 34. It's tiny. Please make sure you read this correctly off your information sheet. You don't need to know it, but you must write it down correctly. Okay, and it's one of those horrible constants. Hopefully by the time you've done enough of these questions, you'll know it anyway. Then, FO is the threshold frequency measured in hertz. It's sometimes called the cutoff frequency. You shouldn't see that one very often, okay? But it has to be in hertz. Generally, we're going to work with very high frequencies because we're working with ultraviolet light, which has a very small wavelength. But we're going to work with this equation lots and lots and lots. I think that is enough information for now, so we're going to take a short break, and I'll see you in a couple of minutes. Welcome back. So we've been investigating the photoelectric effect. We now need to do a little bit more theory because there's some explanations that need to go with it. But we're going to now try and apply what we've learned. Okay, you ready? Let's go. So the first thing I'm going to ask you is, what does the photoelectric effect prove about the nature of light? So, what does it prove? The whole point of the photoelectric effect is that it shows us that light has a particle nature. Okay, so what does it prove? Light has a particle nature. Now, note that I didn't say that light is a particle, because it behaves like a particle, but it also behaves like a wave. It's one of those weird little concepts where, is it actually a particle or is it a wave? Well, it's neither, and it's both, because it depends on the situation. How do I know that it's behaving like a particle? Because when electrons get ejected, there is a collision between the electron and light. Okay. For the electrons to move, light must be behaving as a particle. Particle. There we go. So light is behaving like a particle. Light is both a wave and a particle at the same time. It's not just a wave and it's not just a particle. It's what makes this so hard. But what's happening here is as the light comes, it's like a particle, like momentum. It's colliding with the electron. That collision allows energy from the light to move to the electron, and that energy then allows the electron to move. Okay, so it's like a momentum collision. It's behaving like a particle. So we say it has a particle nature. All right? Now, explain briefly how you would use an electroscope to demonstrate the photoelectric effect. And now some of you are going, but Tracy, we haven't used an electroscope. You've seen electroscopes before, but this is more how we would ask you in exams, okay? So a basic electroscope looks like this, okay? Here at the top there, that's where my zinc plate would be. This is a conducting rod for us. So it's made out of a metal that allows electrons to move. Then this is our conducting plate. And then over here, this little piece there, that's called a gold leaf. What this really is, it almost looks like tin foil, like aluminum foil we use in cooking, but it's gold, and it's very, 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 very thin. They are extremely delicate, okay? But we use them because they can conduct electricity so well, so they can gain charge quickly. What the electroscope allows us to do is look at the movement of charge. First thing we have to do with this is we need to charge the electroscope. So we make the electroscope negatively charged. We're not concerned with how we charge the electroscope. You would have done that hopefully in previous years when you were looking at charging, how the different ways we can charge an electroscope through touch or through induction. We're not worried about that. The point is we've charged it. We've given it excess negative charge. What's important here is that the gold leaf and the conducting plate are away from each other. They're both negative. So we have the gold leaf, they're both negative, so the gold leaf's repelled from the conducting plate. They're not attracted to each other. Why do I want a negatively charged electroscope? Because with the photoelectric effect, I'm looking at how electrons get pushed out. If it's positively charged, the electrons aren't going to want to go anywhere because they're attracted to the positive. So we have excess electrons so that when I shine the correct light onto the electroscope, electrons can come off. But the electrons are only going to come off the zinc plate. Okay? So, what we then do is we shine light onto the electroscope. Okay? And we look for whether the gold leaf drops. So we want the gold leaf to drop. But the gold leaf will only drop if electrons go away. Because if we take electrons off the zinc plate, this becomes less negative. If it's less negative, then they're not going to be as far away. They're going to come down. And if we allow enough electrons to come off, it'll go flat because it'll become neutral. But what are we looking for? The electrons leave the zinc. But here, and they do like zinc, in particular as a metal you should know. This only happens when we have light in the ultraviolet part of light. So it's at the top end of the frequency, so it's a very small wavelength. We can't see ultraviolet light. Sometimes it's called black light. So if you look at TV shows and they shine that purple color light and it allows things to reflect back, it's good for glow-in-the-dark stuff. All right, you see glow-in-the-dark stuff really good. It's called a black light. It's not actually black. It's ultraviolet. So when you can see it with black lights, it's got that violet-y blue hue to it, color to it. The sun gives us UV. That's what gets us sunburnt, is ultraviolet light, okay? But it's a very small wave with a big frequency, and zinc will only allow electrons to move when we shine ultraviolet light onto it. So if we want to demonstrate the photoelectric effect, we have a zinc plate on the electroscope, negatively charge the electroscope, and then shine ultraviolet light on it. The electrons will then move out, and the gold leaf will drop. If we make the light normal light, nothing will happen. The gold leaf will stay where it is. Doesn't matter how bright you make it. You can even make it as bright as the lights we have in the studio. It doesn't make a difference. The intensity of the light, the brightness of the light doesn't matter. It's about the frequency, okay? So, lots of theory, lots to think about. Go back and learn the electroscope because they are going to ask you that. It's one of those nice ones which they sort of wiggle into a paper, okay? We're going to take a short break, and then we'll do some more questions when you get back. See you in a couple of minutes. Welcome back, everyone. We've been doing photoelectric effect, and now we're going to do some calculations with that horrible number of Planck's constant. But it's okay. We can do this. Let's go. So, a group of learners perform an investigation to compare the effect of two types of radiation on the emission of photoelectrons. Now, photoelectrons just means we have any electrons come off from zinc. They place a zinc plate on top of the disk of a negatively charged electroscope. We did that just now. Ultraviolet and red light are shown alternatively on the zinc plate as shown. It's on the next page when the electroscope is fully charged. So here we go. So there's the radiation, there's the zinc plate. We have our disc, we have the gold leaf, and then we put the radiation, we shine light on it. What they see is that with the ultraviolet, the gold leaf collapses. With the red light, there's no effect on the deflection of the gold leaves, so they stay where they are. Now we've got a couple of questions. Write down an investigative question, very important. Explain the observation and what conclusion can be drawn. So, an investigative question is, what are we investigating? You cannot start it with words that will result in a yes or a no answer. So you can't start with these words. Does, is, will, okay, and can. There we go. There's the other one. If I start a question with one of those 4 words, I can answer the question with a yes or a no. For example, will the type of radiation affect electrons being moved off? Yes. That's not what I want, okay? We need to recognize that we're looking at the type of electrons, type of radiation, and where the electrons get emitted. So, what we're going to start with is, how does, I can't answer that with a yes or no, the type of radiation affect the electrons that are emitted from a zinc plate. I've got my variables, the zinc plate and the number of electrons, and I've got the type of radiation. Here, I can't answer this with a yes or a no. I have to answer it with an explanation. It's a question, so we can't start with to determine. It must be a question, must end with a question mark. Now, the other question was explain the observation made for ultraviolet light, and I didn't leave myself enough space, so I'm going to do it here quickly. Why? Electrons are emitted okay? Therefore, electroscope less negative. That's enough. The gold leaf will drop. What conclusion can be drawn from this experiment? Be careful here. You cannot tell me that light is a particle. We've spoken about this already. What you can tell me is that light has a particle nature. It's behaving like a particle. Okay? Great. Now, consider the following information. I did say to you at some stage that you don't need to learn the threshold frequencies of different metals. You do not need to learn their work functions. That's information that either you're going to calculate or they're going to give to you for calculations. Okay? So, the work function of zinc is 6,88 times 10 to the minus 19. It's quite small. The frequency of ultraviolet light is 7,89 times 10 to the 14. And the frequency of red light is 4,39 times 10 to the 14. So this is actually related to the question we just did. First thing is to define the work function. The work function is the minimum energy required is with a Q, not a G, to eject a photoelectron from, now be careful here, the surface of a metal. Now, we can only get the photoelectric effect with a metal because of the way the metal is bonded, because of the delocalized electrons in a metal. But you still need to tell me that it's from the surface of a metal. You can't just say it's the minimum energy to eject an electron. It's very specific, from the surface of a metal. Then they say, use a calculation to explain why red light fails to emit photoelectrons from the surface of the zinc plate. We're going to use the work function of the zinc. So my work function is H times FO. They've told me what the work function is, 6,88. What I'm going to do is I'm going to find the threshold frequency and compare it to red light's frequency. Okay? So we have 6,88 times 10 to the minus 19. Planck's constant you will see on your information sheet, 6,63 times 10 to the minus 34. And I want the frequency. So to get FO on its own, I'm going to take the work function, divide it by Planck's constant. Oh, yes, that's right. Just checking that I'm writing it down right. And we're going to use our calculators. I certainly cannot do this in my head. So we've got 6.88 to the minus, make sure you put them, to the minus 19, divided by 6.63 to the minus 34, and we get 1,0. We're going to round it off to 2 decimal places, so it's 1,04 times 10 to the 15 hertz. Now look, red light has a frequency of 4,39 times 10 to the 14. It's way too small, okay? It will not, the work function, the frequency is too small. So the frequency of red light is smaller than the threshold frequency. If it's smaller than the threshold frequency, nothing can, it won't get ejected. It's as simple as that, okay? Calculate the work function of potassium, which has a cutoff frequency of 5,6. We're going to do this one quickly. So work function is HFO, H 6,63 times 10 to the minus 34 times 5,6 times 10 to the 14. We're definitely going to use, whoopsie, that's not what I wanted to do. Sorry, we're going to use our calculators because these are hard ones in our head. 6.63 to the minus 34 times 5.6 to the 14, and we get 3,71. Let's just check, was that 7,1 or 1,7? Oop, I've done it again. 7,1, okay, good. 7,1 times 10, and now, of course, I can't remember what the other name was. Number, it's minus 19, measured in hertz. Hertz. Am I expecting a small number? Absolutely. Why? Because that's so small. That's tiny. Okay? So, we've done lots. Okay? There's still more to do. But remember, the photoelectric effect proves to us that light has a particle nature. But not just any light can eject electrons. It has to be light of a specific frequency for every metal. Everyone has its own threshold frequency. Okay? And right there is where we're going to stop for now. So I'm going to say goodbye, and I'll see you again next time.